Welcome back to the Deep Dive. Today, we're diving into, well, a really monumental story in physics. It's about understanding atoms and how they interact with light.
Mm-hmm.
We're going from these catastrophic paradoxes that almost broke classical physics
Right.
all the way to the kind of laser precision we see in modern optical physics. It's quite a journey.
It really is. And our mission here is, well, pretty ambitious. We're digging into a whole stack of sources on atomic and laser spectroscopy.
Okay.
We're looking at the classical failures, the big shift to quantum mechanics, and some really surprising experimental techniques that came along, especially up to the mid-70s.
Techniques that let them actually test the theories.
Exactly. But the core theme, I think, is stability. How did we figure out why atoms don't just, vanish in a puff of radiation?
I like that. Stability. Okay, so let's start right at the beginning of that crisis. Rutherford's model, turn of the century.
Right, Rutherford. His model was brilliant in identifying the structure, a heavy positive nucleus, electrons orbiting, like a tiny solar system.
Held together by the Coulomb force. Seems logical.
The structure was fine. The problem was, well, the motion according to classical physics.
Ah. So what did classical physics say about an electron moving like that?
Classical electrodynamics is crystal clear on this. If you have an accelerating charge, it has to radiate electromagnetic energy, period.
And an orbiting electron is always accelerating because its direction is changing.
Constantly. So it should be constantly losing energy, radiating it away as light.
Which means?
It spirals inward fast. It should crash into the nucleus in like a tiny fraction of a second.
So the classical prediction wasn't just wrong, it was spectacularly wrong. It predicted instant atomic destruction.
Complete instability for every atom. And continuous radiation, getting higher in frequency as the electrons spiraled faster. Total disaster, theoretically.
But obviously, atoms are stable. And when you zap them, say in a gas discharge tube, you don't get a rainbow, you get specific lines of color.
Discrete frequencies. Very specific. That was the huge disconnect. The data just screamed that the fundamental physics was missing something big.
Was there a clue hidden in all those spectral lines they were measuring?
There was. Even before Bohr, the spectroscopists noticed a pattern. It got formalized around 1908 by the Ritz combination principle.
Okay, what did that say?
It basically said that the energy, or more precisely the wave number, of any spectral line you measured could always be written as the difference between two numbers, just two specific values, which they called terms.
That sounds structured, like finding out every musical note is related in a simple mathematical way.
Exactly. It strongly hinted that atoms had some kind of internal defined energy structure, and this was confirmed when Paschen found a whole new series of lines in the infrared fitting the same pattern.
Okay, so the stage is set. The classical atom is impossible, but the light coming from atoms suggests hidden rules. Enter Niels Bohr.
1913, Bohr comes in and isn't afraid to just, break the classical rules. He had to.
What were his big moves? His postulates?
He made three huge leaps. First, he just declared that atoms, these bound systems, can only exist in certain special discrete energy levels. E-dollars, E22, and so on. Stationary states.
No spiraling allowed, just fixed states. That deals with stability.
Right. And the second postulate explains the light. Atoms only emit or absorb radiation when they jump between these allowed levels.
A quantum leap.
A quantum leap, exactly. And the frequency, omega, of that light is directly tied to the energy difference. Omega is just 8 minus omega, the difference between the start and end levels.
Okay, that explains the discrete lines in the Ritz principle immediately. The terms are just the energy levels divided by Planck's constant.
Precisely. And his third postulate, specifically for the simple hydrogen atom, gave a rule for which orbits or energy levels were allowed.
How did he pick them?
He proposed that the electron's angular momentum had to be a whole multiple of Planck's constant over 2 π. From a classical view, this was completely arbitrary, just pulled out of thin air almost.
But it worked.
It worked beautifully for hydrogen. It explained the known spectral series, predicted others, and gave a theoretical basis for the Ritz combination principle. It turned the chaos into order.
Revolutionary. But as you mentioned, this old quantum theory had its limits. It kind of stumbled when things got more complicated, right? Like trying to calculate helium.
Oh, absolutely. It couldn't handle multi-electron atoms properly. It was more like a brilliant patch than a complete theory. The real foundation came later, between roughly 1924 and 1939.
The new quantum mechanics.
Yeah, with de Broglie and his matter waves, Schrödinger's wave equation, Heisenberg's matrix mechanics. It was a complete overhaul. And by 39, Dirac had his relativistic theory, including electron spin.
Which seemed like it should be the final answer, at least for hydrogen.
It really felt that way for a while, and underpinning all this was the correspondence principle. That was crucial.
Remind us what that is.
It's basically a reality check. It says that as you look at quantum systems in the limit of large quantum numbers, big orbits, high energies, the quantum predictions must merge smoothly and agree with classical physics.
So the weird quantum rules have to somehow turn back into the familiar classical rules when things get big enough.
Exactly. It prevents quantum mechanics from being completely disconnected from the world we experience. It acts as a bridge.
But even Dirac's elegant theory wasn't quite the end of the story for hydrogen. The next twist came, surprisingly, from wartime tech.
That's right. World War II spurred huge advances in radar and radio technology, especially microwaves. After the war, scientists had these amazing new tools to probe atomic energy levels with incredible precision.
And that led to
The Lamb shift experiment in 1947. Willis Lamb measured a tiny energy difference between two specific states in hydrogen, the 2s12 and 2p12 states.
And Dirac's theory predicted
That they should have exactly the same energy. They should be degenerate. But Lamb found they weren't. There was a small split, about a gigahertz in frequency terms.
tiny, but theoretically huge.
Absolutely shattering for the existing theory. It showed Dirac's equation, elegant as it was incomplete. It wasn't accounting for something subtle happening within the atom.
The quantum vacuum itself, right? Interactions with virtual particles.
Precisely. It turned out the electron wasn't just interacting with the proton's field, but also with the fluctuating electromagnetic field of the vacuum itself. This tiny discrepancy spurred the development of quantum electrodynamics, QED.
Which could calculate these effects, these radiative corrections.
Yes, QED provided the framework to handle these vacuum interactions and calculate the Lamb shift with remarkable accuracy. It was a major triumph.
While QED was tackling the theory, experimentalists were also making huge strides in manipulating atoms. Wasn't Alfred Kassler in Paris a key figure?
Oh, definitely. Kassler and his group, starting around 1949 or 1950, invented incredibly clever techniques like optical double resonance and, crucially, optical pumping.
Optical pumping. Sounds like you're using light to pump something.
In a way, yes. You're using carefully chosen polarized light to selectively excite atoms and transfer angular momentum to them, essentially pumping them into specific desired quantum states. It gave experimenters unprecedented control over atomic populations before they even started their measurements.
So you could prepare a sample of atoms all lined up, ready for study.
Exactly. These methods allowed for extremely precise studies of things like hyperfine structure and other subtle atom-light interactions. It was a golden age for experimental ingenuity.
And then came the ultimate tool for interacting with atoms, the laser.
The laser just changed everything. Following the invention of the maser, the laser provided a light source that was intense, directional, and incredibly pure in frequency.
Which opened up completely new areas.
Immediately, you had people like Franken demonstrating frequency doubling, turning red laser light into blue, which kicked off the whole field of nonlinear optics. But for spectroscopy, the huge breakthrough was the tunable dye laser around 1970.
Tunable meaning you could pick the exact color you wanted.
With exquisite precision. Suddenly, you could tune your laser right onto a specific atomic transition, excite just that one level, and study it cleanly. This led to an absolute explosion in high-resolution atomic physics research.
The laser gave us the precision light source. Okay, let's shift gears a bit and talk about measuring time specifically. How long these excited states actually last. Their lifetimes.
Right, radiative lifetimes. Knowing these values and the related transition probabilities is really fundamental. It's not just pure science. Astrophysicists need these numbers to model stars, nebulae.
Plasma physicists need them too.
Absolutely. It governs how energy moves around in hot gases.
One method you mentioned from the sources sounds pretty intense, the beamfoil method.
It is intense. It's designed to study atoms that are missing lots of electrons, highly ionized species. You can't easily make or keep those stable in a normal lab setup.
So how does it work? You shoot ions through a foil.
Yeah, you take a beam of ions, say nitrogen ions, accelerated to incredible speeds, maybe 5 million meters per second, really moving. And you fire this beam through an incredibly thin carbon foil. We're talking maybe 25 to 200 nanometers thick, just gossamer thin.
What happens when they go through the foil?
They interact violently, electrons get stripped off, and the ions emerge on the other side in various states of high excitation and high ionization. Then they fly into a drift tube with a very good vacuum, maybe 10 Dalton torr, so virtually no collisions. The excited ions just decay naturally by emitting photons.
And you measure that light, but how do you get the lifetime?
This is the clever part. You know the speed of the ions very precisely. So you measure the intensity of the emitted light as a function of distance down the tube from the foil. Since speed is constant, distance directly translates to time elapsed since excitation.
Wow. So the ruler becomes the clock.
Exactly. It's a brilliant way to measure lifetimes, especially for short-lived states and ions you couldn't study otherwise. It avoids problems like collisions or radiation trapping that you might get in a denser gas cell.
Are there downsides? Challenges?
The main one is often low light levels. But analytically, the big headache is radiative cascade.
Cascade, meaning?
Meaning the energy level you're watching might be getting repopulated by decays from even higher energy levels that were also excited by the foil. So the light decay you measure isn't a single clean exponential decay.
Ah, it's a sum of decays.
Right. You see a curve that's a sum of several exponentials corresponding to the direct decay plus the feeding from higher states. You need careful analysis to disentangle the lifetime you actually want.
Okay, so beam foil is high energy, good for ions, deals with cascades. What's a contrasting method? Maybe something using those new pulsed light sources.
A perfect contrast is the delayed coincidence technique. This is much more gentle and precise for neutral atoms or low ionization states.
How does that work?
You use a very short pulse of light, maybe from a pulse laser or shaped using something like a fast Kerr cell shutter to excite your sample, let's say sodium vapor, to a specific state, like the 32 pialar levels using the yellow D lines.
You hit it with a quick flash of light.
A very quick flash. And at the same instant that pulse hits the atoms, you start a very precise timer. Then you simply wait for a photon to be emitted as the atom decays, and you stop the timer when that photon hits your detector.
So you're directly timing the gap between excitation and decay, photon by photon.
Exactly. By collecting data from many such events, you build up a histogram of decay times, which directly gives you the exponential decay curve and the lifetime.
And the precision.
Really remarkable. Because you're using fast electronics triggered by single photons, you can achieve accuracies down to the nanosecond or even sub-nanosecond range. We're talking maybe 1 part in a billion seconds accuracy. Much cleaner signal than beam foil generally, if you can use it.
Fantastic precision. Now let's get into something even more subtle. The forbidden transitions. We know the default decay is electric dipole radiation, E1. And that has rules, right? Selection rules involving parity.
Yes, parity is a fundamental quantum mechanical symmetry. Think of it like looking at the atom's wave function in a mirror. If reflecting it through the origin changes the sign of the wave function, it has odd parity. If it stays the same, it has even parity.
Okay.
The main selection rule for the standard fast E1 transitions is that the initial and final states must have opposite parity. Odd to even, or even to odd.
So if both states have the same parity, say even to even, then the E1 transition is
forbidden. It just can't happen via that mechanism. The quantum mechanics forbids it.
But the atom is still in an excited state. It has to get down somehow eventually.
Yeah, right. If E1 is blocked, it has to resort to much, much slower processes. Typically magnetic dipole, M1, or electric quadrupole, E2 transitions. These have different selection rules, including allowing same parity transition.
And these are the forbidden lines.
Those are the forbidden lines. And the crucial point is their speed. They are thousands or millions of times slower than allowed E1 transitions.
So slow that you usually don't see them in the lab?
Pretty much. In a typical lab experiment with reasonable gas pressure, the excited atom will almost certainly bump into another atom and lose its energy through a collision long before it gets a chance to emit that slow, forbidden photon.
But out in space, or in very thin plasmas?
Ah, that's where they shine, literally. In the near vacuum of space or the extremely low densities of things like the Earth's upper atmosphere or the solar corona, collisions are rare.
So the atoms have time to wait.
They have all the time in the world, relatively speaking, to decay via these slow, forbidden channels. And that's why these lines become prominent.
You mentioned the aurora, the northern lights. That green color.
It's that famous eerie green glow at 55577 angstroms. That's a forbidden transition in atomic oxygen, an
Wow.
M1 transition, actually.
Yeah.
And the red aurora you sometimes see around 6300 angstroms, also forbidden oxygen lines involving E2 as well.
Amazing. We're seeing quantum selection rules painted across the night sky.
Exactly. And in the solar corona, the sun's incredibly hot, thin outer atmosphere, you see forbidden lines from highly ionized atoms, things like calcium missing 11 electrons. These lines are essential diagnostic tools for astronomers. They tell us about the density, temperature, and composition of these extreme environments where normal lines might not be efficiently excited.
It's like the universe provides the perfect laboratory conditions to see these fundamental but slow processes. But what if all single-photon routes are forbidden, even M1 and E2?
Then you get into even stranger territory. The atom might be forced into decaying by emitting 2 photons simultaneously.
2 photons at once. How does that work?
It's a higher-order quantum process. The 2 photons together carry away the total energy difference between the initial and final states. And crucially, they can also together carry away the necessary angular momentum and satisfy parity rules that a single photon couldn't.
So it's a way to conserve everything when the simpler options are blocked.
Exactly. The classic example is the decay of the first excited state of hydrogen, the 22s12 down to the ground state, 12s12. Both are s states, same parity, zero change in orbital angular momentum. Single photon emission is strictly forbidden.
So hydrogen's $2 a Rees state has to decay this way.
In isolation, yes. It decays by emitting 2 photons that share the energy. This was actually worked out theoretically way back in the 30s by Guppert-Meyer and applied to hydrogen by Bright and Teller in 1940.
Is this 2-photon decay common? Fast? Slow?
Incredibly slow for hydrogen. The lifetime of the $2 sedate against 2-photon decay is about 1/8 of a second, which sounds short, but it's vastly longer than typical allowed transitions.
And you mentioned this depends strongly on the atom.
Hugely. The rate goes roughly as 66x, where Z is the atomic number, the number of protons.
Z to the 6th power? That's an enormous dependence.
It really is. So while it's very slow for hydrogen, Z1, if you look at the same transition in, say, highly ionized krypton, Z36, that SID Z66 factor makes the 2-photon decay billions of times faster. The rules of stability completely change depending on the nucleus.
What a journey. We've gone from Rutherford's atom flying apart through Bohr's ad hoc rules to the full machinery of quantum mechanics and QED, and ended up looking at these incredibly subtle, slow decay processes.
And the amazing thing, looking back from that mid-70s perspective captured in our sources, is how stunningly successful the theory became. Quantum mechanics, boosted by QED for those fine details like the Lamb shift, really does seem to explain pretty much all the features of atomic and molecular energy levels and transitions.
That stability that seemed so paradoxical in 1900 was finally understood through these precise quantum rules.
Exactly. It rests on discrete energy levels and strictly governed transitions between them.
Okay, as we wrap up this deep dive, here's something to think about. We talk about that metastable 22s12 in hydrogen, decaying by that rare 2-photon process. Now, in the lab, you said collisions usually kill that state long before it can decay.
Collisions are usually dominant.
But out in the near-perfect vacuum of interstellar space, collisions basically stop happening. An atom can drift for years between encounters.
Yeah.
Our sources note that for ionized helium, He plus A, which is hydrogen-like, the 2-photon lifetime is still very long, about 5 milliseconds. So think about this. Out there in the void, these incredibly slow, fundamental quantum processes, the forbidden decays, the 2-photon emissions, they aren't just curiosities. They become the main pathways dictating how atoms release energy and how long they live in excited states.
Correct.
So when we observe those forbidden lines from nebulae or the aurora, what are they really telling us about how quantum mechanics asserts its fundamental rules over vast timescales across the emptiness of the universe?
A fascinating question. The universe as the ultimate quantum lab.
Until next time. Indeed. Until next time, keep digging.